In this video, we're going to discuss polarity, intermolecular forces, and states of matter. So we've discussed ionic bonds and how ionic bonds are generally a cation surrounded by anions to form a crystal, and anions surrounded by cations to form a crystal. This is by nature a polar system forming these solids because you have electrostatic interactions holding these crystals together. And that's what causes these types of compounds to be mostly solids, except at extremely high temperatures. But we haven't discussed what happens when you have a covalent bond. So if you have a covalent bond between two of the same atoms, here we have chlorine gas, a molecule of chlorine gas, and chlorine, atoms of chlorine will bond with another atom of chlorine. And the greediness of these two atoms is roughly equivalent. And so the electrons are shared equally. But there are some compounds where you have two elements, and these two elements have different greediness towards electrons. And that greediness, the term that we use for it is electronegativity. That's an element's pull on electrons in a covalent bond while bonding. Now, chlorine, being on the right-hand side of a periodic table, is about the third greediest element there is, or the third most electronegative element there is. And so when we draw the electron cloud for this compound, we're going to see that there's a very small amount of electron density on the hydrogen side, and there's a much greater amount of electron density on the chlorine side. Basically, we would say that this is a polar compound or polar bond where electrons are not shared equally. And so we actually would draw a little positive charge here and a little negative charge here to show that over here, this part of the molecule is much more negative than this part of the molecule. And we can look at the same basic principle with water. If we have oxygen, the oxygen is making bonds with hydrogens, and we draw an electron cloud around this structure showing where the electron density is. We would see that we would have very little electron density around our hydrogen and a great deal of electron density. So this would be very, very thick here around our oxygen. And so this has got a much more negative charge. It's got, if we think about electron density as we have some electrons that are in these bonds, and a dollop of jam represents these electrons, then the jam is going to be much thicker on this part of the molecule than it is going to be over here. And it's going to be thin enough on this side that we can actually see the nucleus's positive charge coming through that layer of jam. And so that means that we have a partial positive charge over here and a partial negative charge on this side. Now, depending on how polar this molecule is, so we're going to describe water as a polar molecule, and indeed most biological molecules are polar, which makes water a very good solvent, because there's a rule that we talk about in chemistry that like dissolves like. And so if you have a polar molecule like water, it will dissolve polar molecules like proteins and sugars and carbohydrates and DNA and all of those very important biological molecules that we need to survive. Polarity is responsible for all the forces that hold molecules together. And I'm not talking about the bonds that are internal to the molecule. I'm talking about the forces that keep molecules in general. So one molecule, why is it next to the neighboring molecule? Why does it stay stuck there? Why is it a liquid versus a gas versus a solid? Those types of intermolecular forces. So intermolecular forces are forces between separate molecules. Now, we have another term that's sometimes used that is intramolecular forces, and these would be forces inside molecules. Intramolecular forces are the forces that basically determine the state of matter. There are 3 types of intermolecular forces. The first type is dipole-dipole interactions. Dipole-dipole interactions is simply when you have one polar molecule and it has a positive side and a negative side, and we'll use our little deltas to say it's a partial positive charge and a partial negative charge, attracted to a second polar molecule with its partial positive side and partial negative side, and the partial positive side is attracted to the partial negative side of the neighboring molecule, and you have electrostatic forces, the plus and the minus, want to get together and have these 2 molecules stick together. Just the act of having this partial positive and partial negative, this is a dipole, and so any molecule that has a dipole can interact with another molecule that has a dipole, and that's called dipole-dipole interaction. So dipole-dipole interactions keep molecules together by having positive ends and negative ends of the different molecules attracted to each other, making these formations and keeping the molecules together. The next type of intermolecular force is hydrogen bonding. And this is the strongest type of intermolecular force. And this is the one that is responsible for the very strong surface tension and many of the other really neat properties that water has. As we discussed earlier, water has dipoles. It has an oxygen atom bonded to 2 hydrogen atoms. The gradiness of oxygen is much higher than that of hydrogen, so it's more electronegative. And it also has 2 pairs of non-bonding electrons, which are electrons that are not involved in bonding. They're only associated with the nucleus of the oxygen, and so they don't have another nucleus on the other side of them. And so they're basically bits of negative charge that are hanging off of this oxygen atom. And then we also stated that there was a partial positive charge here on the hydrogen, and from this bond there is a partial negative charge where the oxygen is. So there's kind of a double whammy here as positive and negative bonds. But the other thing that makes water kind of special is that the size of the orbitals here of these hydrogens. They're mostly empty now because the oxygen has stolen quite a bit of the electron density. Another neighboring compound or molecule, let's say oxygen, could put the lone pair of electrons that it has, and it has an orbital that has those electrons, and they line up very nicely with this electron deficient orbital here on the hydrogen. And so you get a very special intermolecular force here that occurs, which is called hydrogen bonding. And it's more than just a dipole-dipole interaction. It has a specific geometry. And because it has a specific geometry, when water molecules line up in a solid, in a very rigid structure, they actually spread out versus how they are in their liquid state. And so when they're not moving enough to break free, they'll line up so that there are quite large air gaps in between the water molecules, and this causes the phenomenon that ice is one of the few solids that is less dense than its liquid form of liquid water, which is very, very good for biological systems in general, because if ice sank to the bottom of all oceans and lakes, then what would happen was all the waterways would freeze solid and biological systems wouldn't be able to function in the liquid environment underneath like it does now. So because ice floats, it forms like an insulating layer and manages to stop that a bit. And it's this hydrogen bonding phenomenon that water is especially well geared to undergo because of its dual set of lone pairs and dual set of hydrogens that can accept those lone pairs, that we get this interesting phenomenon with ice floating on top of water. Beyond this hydrogen bonding causing ice to float on top of water, it also means that compared to other liquids, water has a high boiling point and it has a high surface tension and it has wonderful dissolving power for biological molecules, which also have the potential for hydrogen bonding. In order for hydrogen bonding to occur, you must have a hydrogen attached to a nitrogen, oxygen, or fluorine. And then the atom that is participating in donating a non-bonding pair of electrons to those hydrogens must also be on a nitrogen, oxygen, or fluorine. So we will get groups of molecules where we have these systems of hydrogens and oxygens where we get these overlaps. And these networks of hydrogen bonds allow different structures to form very, very high boiling situations. Also, hydrogen bonds are what keep the two neighboring DNA strands of the famous double helix together. It causes a lot of the structure of proteins to be the way that it is. And so hydrogen bonding is a very important intermolecular force in nature. The third intermolecular force is probably the hardest to explain, and this is dispersion forces. And dispersion forces occur in every situation. So every type of atom has dispersion forces, polar or nonpolar. But in polar molecules, we have dipole-dipole interactions, and in the right circumstances, we also have hydrogen bonding. So really, dispersion forces only shine in nonpolar compounds. Let's say, for instance, that we have propane, and the electronegativity difference between the hydrogen and the carbon atoms in propane are not very large. Realistically, there isn't a significant dipole here between the hydrogen and the carbon because their electronegativities are very, very close. And since their electronegativities are very, very very close, you don't really see a lot of dipole interactions in a compound like this. And of course, there's no greediness difference between a carbon and another carbon because the electronegativity of one type of atom is the same as the electronegativity of a different atom of that same element. And so consequently, we don't expect that compounds like propane would have very high dipole-dipole interactions, if any at all. And yet, propane is a liquid. There must be some kind of intermolecular force that's holding these molecules together, causing it to become a liquid. And what happens is that at any given period of time in a bond, the electrons will suddenly go to one side of the bond versus another side of the bond. So if we say that this is our bond and normally we would have an even distribution of jam, then what happens is on some occasions we don't have an even distribution, and we would have all of the electron density because the electrons are moving. Statistically, they're going to exist on one side more than on the other side. And so when this happens, we get what we call an instantaneous dipole. It doesn't last very long, but basically it's like both the electrons in the bond suddenly went to one side, and they left kind of a hole here on this other side of the molecule, leaving a partial positive charge over here versus over here. Now, what happens is when the next door molecule comes by and it was evenly distributed, but then suddenly it sees this positive charge, and the electrons will move towards that positive charge because they're attracted to it. They'll leave kind of a hole on this other side. And then what we've done is we've created a partial negative charge on this side and a partial positive charge on this side. When the next door molecule sees it, its electrons, which were evenly distributed, notice the negative charge over here. Negative charges find other negative charges literally repulsive. This electron density is going to go more away from those electrons. It's going to leave a hole over here, which it finds attractive to this negative charge, and so on and so on. And this is how we get these dispersion forces occurring. And they will suddenly all disappear and go away as if they weren't there, and another set of dispersion forces will propagate throughout molecules. Now, this type of instantaneous dipole that we've discussed over here can occur in every single bond of a molecule. The more bonds you have in a molecule, the higher the tendency it is to have these dispersion forces. What you'll notice is that the larger a molecule is, or the more bonds it has, the more tendency it has to become a solid. So if we have CH4 that has 4 bonds in it, that's a gas. But if we have C2H4, which has this many bonds in it, that's still a gas. But it has a higher boiling point, so it stays a liquid at higher temperatures than methane does. Okay, so the boiling point's increasing as the number of bonds increase. And then finally, we have propane, which is now a gas at room temperature, but it's fairly easy to bottle in liquid form, and that's where we get our propane tanks from. And then finally, when we get to butane, butane has 4 carbons, and it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bonds. This one is a liquid at room temperature because it has more dispersion forces. So the stronger the intermolecular forces, the more organization you're going to see in the compound, and the more heat it requires to disrupt it. So the higher the boiling point, the higher the melting point, the stronger the intermolecular forces. The strongest intermolecular forces from strength perspective, you have hydrogen bonding is the strongest, dipole-dipole is the second strongest, and dispersion is the weakest. Here we have the review questions for this. Please take some time, pause your video, work on the questions, and I will return in 10 seconds to discuss the answers. So what type of intermolecular forces does water have? Water has them all. It has dispersion forces because it has covalent bonds. It has dipole-dipole interactions because it has dipoles. And it has hydrogen bonding because it has an oxygen with hydrogens attached. So it has all three types of intermolecular forces. Which is the strongest intermolecular force? Hands down, it's hydrogen bonding, because hydrogen bonding actually has some orbital overlap. And that orbital overlap, or the electron clouds of the neighboring molecules merging, allows it to be the strongest of the intermolecular forces.